Bismillahirrahmanirrahim. Welcome to Applied Thermodynamics by McConkey with Dr. Abid Hussain. In this lecture, we are solving problem 4.13. So, problem is 0.06 meter cube of ethane, molar mass 30 kilogram per kilomole at 6.9 bar and 260 degrees centigrade is allowed to expand isentropically in a cylinder behind a piston to a pressure of 1.05 bar and temperature of 170 degrees centigrade. So first I write given data, and given data initially volume V1 is equal to 0.06 cubic meter. Working fluid is ethane and molar mass of ethane is 30 kilogram per kilomole at 6.9 bar. Initial pressure P1 is equal to 6.9 bar and T1 is equal to 260 degrees centigrade. T1 is equal to 260 degrees centigrade, which is equal to 260 plus 273 Kelvin, and 260 plus 273 is equal to 533 Kelvin, is allowed to expand isentropically. Process is isentropic expansion, and the second name of isentropic expansion is adiabatic expansion. We can write this as S1 is equal to S2 or PV gamma is equal to C. This is isentropic or adiabatic process. And this is behind a piston to a pressure of 1. After expansion, pressure decreases. So pressure decreased to 1.05 bar and temperature T2 decrease from 260 to 107 degrees centigrade, and 107 degrees centigrade is equal to 107 plus 273 Kelvin, which is equal to 390 Kelvin, 380 Kelvin. Calculate gamma. Required is gamma R ideal gas constant, number 3 Cp, number 4 Cv, number 5, this is number 4, number 5, and calculate the work done during the expansion, and assume ethene to be a perfect gas. So we will use perfect gas equation. And second process, now second process started from here. The same mass of ethane at 1.05 bar 100 degrees is compressed, second process, to 6.9 bar according to LA PB 1.4 is equal to constant. So second process is compression according to LA PV power 1.4 is equal to C. And in compression, pressure increases, so pressure from P2 1.05 bar to P3 is equal to 6.9 bar. It means that pressure increases from 1.05 bar to 6.9 bar according to LA. Calculate the final temperature of the ethane. Required is, in the second part, required is number 1 final temperature T3. Calculate final temperature T3. Number 2, the heat flew 2 hours from the cylinder Q. Find Q. And number 3, calculate also the change of entropy. Calculate the final temperature of the ethane and the heat flew 2 hours from the cylinder wall during the compression. Calculate also the change of entropy during the compression. S3 minus S2. Change in entropy per second process. S3 minus S2. And sketch the process on PV and TS diagram. PV diagram and TS diagram for both processes. First process is isentropic expansion and second process is compression according to law PV power 1/4 is equal to constant. So solution, we can draw PV and TS diagram. So this is PV diagram, pressure and bar and volume and meter cube or n meter cube per kg. Second is TS diagram, temperature and degree centigrade and entropy and kilojoule per kilogram per Kelvin or kilojoule per Kelvin. So first process is isentropic expansion. So initially pressure P1 is equal to 6.9 bar. Initially pressure is 6.9 bar and final pressure is P2 is equal to 1.05 bar and process is adiabatic expansion. So adiabatic expansion is from 1 to 2 is some like this, from 1 to 2. This is adiabatic expansion. P V power gamma is equal to C, or we can write S1 is equal to S2. And second process is process according to a law PV 1.4. PV 1.4 to from 1.05 bar pressure to 6.9. So again the process this line to 6.9 bar. This is 0.3 and here pressure is P3 which is equal to P1. So this is PV diagram for both the process. Now we are drawing, and this process is PV 1.4 is equal to C. Now we draw TS diagram. So we know that initial temperature, this is constant temperature line. Initial temperature is T1 is equal to 260 degrees centigrade. This is T1. And final temperature for the first process T2 is equal to 107 degrees centigrade. This is T2. And we know that constant entropy process is straight vertical line on TS diagram. So this is point 1 and this is point 2. And we can draw constant pressure line. This is constant pressure line. This is constant pressure line. This is constant pressure line and this is second constant pressure line, and this is constant temperature line and this is second constant temperature line. Now process 1 is straight line. Process 1 is straight line isentropic process from 1 to 2, and second constant pressure line passes from this point. This is constant pressure line. So process 1 is, this is point 1 and this is point 2, because initial temperature T1 is 260 and second for the process 1 final temperature is 107 degrees centigrade. This is at the isentropic process S1 is equal to S2, or we can write PV gamma is equal to C. And second process is from 2 to 3, and second process is from 2 to 3, and pressure increased to 6.9 bar. This line is for here, for this line P1 is equal to P3 is equal to 6.9 bar, and this line P2 is equal to 1.05 bar. So this is point 3. So first process is from 1 to 2 isentropic expansion, and second process is from 2 to 3 compression according to a law PV 1.4 is equal to constant. So this is PV diagram and this is TS diagram. Now we are solving the problem. So initially when we solve part first, solve process 1, solution of process 1. So for process 1 we have to find gamma, Cp, Cv, R. So first we find R. So we know that R is equal to molar gas constant divided by molar mass. Molar gas constant is equal to 8.314 kilojoule per kilomole per Kelvin, divided by molar mass is equal to 30 kilograms per kilomole per kilomole. So kilomole will be cancelled with kilomole. So the answer of R will be 0.277 kilojoule per kilogram per Kelvin. Kilojoule per kilogram per Kelvin. So this is R. Now we can find gamma by using the equation T2 divided by T1 is equal to P2 divided by P1 gamma minus 1 divided by gamma. So this implies that T2 or we can write this equation as T1 divided by T2 is equal to P1 divided by P2. So T1 is equal to 533 Kelvin divided by T2 is 380 Kelvin is equal to P1 is equal to 6.9 bar and P2 is equal to 1.05 bar. Whole power gamma minus 1 divided by gamma. So Kelvin will be cancelled with Kelvin, bar will be cancelled with bar. So this implies that 533 divided by 380 is equal to 1.4026. 1.4026 is equal to 6.9 divided by 1.05 is equal to 6.5714. 6.5714 power gamma minus 1 divided by gamma. So this implies that for solution of this problem, take natural log of both sides. So natural log of 1.4026 is equal to natural log of 6.5714 power gamma minus 1 divided by gamma. So this implies natural log of 1.4026 is equal to 0.3383. 0.3383 is equal to, according to the law of logarithm, we can write gamma minus 1 divided by gamma and coefficient. So gamma minus 1 divided by gamma, and natural log of 6.5714 is equal to 1.8782. 1.8782. Now we are further solving this problem. So gamma minus 1 divided by gamma is equal to 0.3383 divided by 1.8782, which is equal to 0.18. So this implies cross multiply. So gamma minus 1 is equal to 0.18 gamma. Or rearrange this equation. So gamma minus 0.18 gamma is equal to 1. So this implies that 0.82 gamma is equal to 1. Or both sides divided by 0.82. So gamma is equal to 0.1 divided by 0.82. So gamma is equal to 1.219. This is the value of gamma. Now we are finding Cp and Cv. As we know that Cp minus Cv is equal to R. So this implies that Cp minus Cv is equal to, the value of R is 0.277 kilojoule per kilogram per Kelvin. This is equation number first. And Cp divided by Cv is equal to gamma. So this implies that Cp divided by Cv is equal to, the value of gamma is 1.219. So this implies that Cp is equal to 1.219 Cv. Now put this value in equation number first. Put a Cp is equal to 1.219 Cv in equation number first. So 1.219 Cv minus Cv is equal to 0.277 kilojoule per kilogram per kilo. Now 1.29 Cv minus 1 Cv is equal to 0.219 Cv is equal to 0.277 kilojoule per kilogram per Kelvin. So this implies that Cv is equal to, both are divided by 0.219. So Cv will be equal to 1.265 kilojoule per kilogram per Kelvin. Put put this value, put in equation number first. So Cp minus 1.265 kilojoule per kilogram per Kelvin is equal to 0.277 kilojoule per kilogram per Kelvin. So Cp is equal to 1.265 kilojoule per kilogram per Kelvin plus 0.277 kilojoule per kilogram per Kelvin. So this implies that Cp is equal to 1.265 plus 0.277 is equal to 1.542 kilojoule per kilogram per Kelvin. This is the value of Cp. Now the required things in first part are gamma, R, Cp, Cv, and now we are finding work done. So for work done, first we find mass. We know that mass is equal to P1 V1 divided by RT1. P1 is equal to 6.9 bar and 1 bar is equal to 10 power 5 Newton per meter square. V1 is equal to 0.06 cubic meter. R is equal to 0.277 kilojoule. Kilo is equal to 10 power 3 and joule is equal to Newton meter per kilogram per Kelvin. Multiply by T1 is equal to 533 Kelvin. So Newton will be cancelled with Newton. This meter and meter square, this is per meter and this is this is per meter and this is per meter square equal to meter cube will be cancelled with this meter cube. This Kelvin will be cancelled with Kelvin. So answer will be, simplify this. This is simple calculation. So mass will be equal to 0.271 kilogram. Now work done is equal to mu2 minus u1, which is equal to m u is equal to cpt. So u2 is equal to cv minus cvt1, which is equal to m cv is common in both, mcv t2 minus t1. Putting values in this, so m is equal to 0.271 kilogram multiplied by cv is equal to 1.265 kilojoule per kilogram per Kelvin, and T2 is equal to 380 Kelvin minus T1 is equal to 533 Kelvin. So W is equal to 0.271 multiplied by 1.265 is equal to 0.3428. This kilogram will be cancelled with this kilo. So this unit will be kilojoule per Kelvin. And 380 minus 533 is equal to minus 253 Kelvin. This Kelvin will be cancelled with this Kelvin. So multiply these two values. Answer will be minus 86.73 kilojoule. So negative sign means that work output or work done by the system or work of expansion is equal to 86.73 kilojoule. Now we are solving second part of the problem. So for second process, first we find final temperature. So for final temperature we use formula T3 divided by T2 is equal to P3 divided by P2 power n minus 1 divided by n. And second process is PV 1.4 is equal to C. It means that this is PV n is equal to C. It means that n is equal to 1.4. So T3 is equal to, the value of T2 is 380 Kelvin and P3 is equal to 6.9 bar and P2 is equal to 1.05 bar. The value of n is 1.4. 1.4 minus 1 divided by 1.4. So T3 is equal to 380 Kelvin. Bar will be cancelled with bar. 6.9 divided by 1.05 is equal to 6.57. 6.57 and power 1.4 minus 1 divided by 1.4 is equal to 0.2857, which is equal to 380 Kelvin multiplied by 6.57 power 0.2857 is equal to 1.71229. So T3 is equal to 650.67 Kelvin. In degree centigrade, subtract 273 from this. So in degree centigrade, this value will be 377.67 degree centigrade. This is final temperature. Now we are finding work done and for the second process. So work done is equal to P3 V3 minus P2 per second process divided by n minus 1. P3 V3 is equal to mr T3 and P2 V2 is equal to mr T2 divided by n minus 1, which is equal to mr is common, so mr T3 minus T2 divided by n minus 1. Now putting values, so work done is equal to m is equal to 0.271 kg, and both process mass is same. This is given in the statement of the problem, that in both process mass is same. R is equal to 0.277 kilojoule per kilogram per Kelvin, and T3 is equal to 6. This is T3. 650.67 Kelvin minus T2 is equal to 380 Kelvin divided by n minus 1. The value of n is 1.4. So work done is equal to, this kilogram will be cancelled with this kilogram. 0.271 multiplied by 0.277 is equal to 0.075 kilojoule per Kelvin, and 650.67 minus 380 is equal to 270.67 Kelvin. Kelvin will be cancelled with Kelvin, and 1.4 minus 1 is equal to 0.4. So now this is simple. Multiply those two values and divide by 0.5. So work is equal to 50.75 kilojoule. So this is work input or work done on this system. Work input, work of compression, or work done on the system. Now we have to find heat flow to R from the system. So Q plus W is equal to U2 minus U1. U2 is equal to mCV T2 and U1 is equal to mCV T1. mCV is common, so mCV T2 minus T1. Now putting values, so Q plus W, the value of W is 50.75 kilojoule is equal to, the value of mass is 0.271 kilogram. CV is equal to 1.265 kilojoule per kilogram per Kelvin, and this is T3 per second process. This is T3 minus T2. So T3 is equal to 650.67 Kelvin minus 380 Kelvin. So Q plus 50.75 kilojoule is equal to 0.271 multiplied by 1265 is equal to 0.3428 kilojoule per Kelvin. This kilogram will be cancelled with kilogram. And 650.67 minus 280 is equal to 270.67. Now Q plus 50.75 kilojoule is equal to this is Kelvin. This Kelvin will be cancelled with this Kelvin. 0.3428 multiplied by 270.67 is equal to 92.79. So Q is equal to 92.79 minus 50.75 kilojoule is kilojoule, and this is kilojoule. So Q is equal to 42.04 kilojoule. Positive sign means that heat is supplied. This is heat supplied. Now the last requirement is that find S3 minus S2. S3 minus S2. So as first process is isentropic. First process is a isentropic. Isentropic mean that S1 is equal to S2. So we can write here S1 instead of S2. So S3 minus S2 is equal to S3 minus S1. I can write here S1 instead of S2. So for S3 minus S1, formula is MCP natural log of T3 divided by T1. T3 divided by T1. So S3 minus S2 is equal to, the value of M is 0.271 kg, 0.271 kg, multiply by the value of Cp is 1.5442 kilojoule per kilogram per Kelvin, multiply by natural log of the value of T3 is 650.67 Kelvin divided by 533. T1 is equal to 533 Kelvin. So S3 minus S2 or S3 minus S1 is equal to 0.271 multiplied by 1.542 is equal to 0.417588. 0.417588. Kilogram will be cancelled with kilogram. This is kilojoule per kilogram. And natural log of 650 divided by 533 is equal to 0.1994. 0.1994. So final answer will be S3 minus S2 or S3 minus S1 is equal to 0.0833 kilojoule per Kelvin. So positive sign means that entropy is increases. So increase in entropy is equal to 0.0833 kilojoule per kilogram. And problem 4.13 is completed. And for more problems, please like and subscribe my YouTube channel and share with your friends. Thank you.